All right, so in this video, we're going to talk about line integrals. This will be kind of a brief introduction, and we'll get into more of the details later on. But right now, we're just going to start off by saying let R, which is a vector valued function, be a smooth parameterization of curve C. And so the line integral setup will look something like this, where we're integrating over curve C, function with respect to x, y, and z, ds. The s there is going to be for arc length, but this is going to translate into this guy right here. Where we have our function evaluated at r of t. We've got the magnitude of r prime, which is the magnitude of the velocity vector, and then with our r of t and r prime of t being here, of course we'll be integrating with respect to t. Now, one of the most common questions that comes along with this is, well, what in the world is a line integral? And so I found this really nice video. It's actually on Wikipedia that will relate what it is we're talking about here in the equation versus what it is we're actually going to be finding. All right, so this is a video from Wikipedia. We've got our surface F right here. We've got our curve C. Here's our curve C from A to B. Now they're taking it and they're manipulating it so that it's a little bit more intuitive and it connects ideas from integrals that we've studied from day one. There are going to be many applications of these line integrals, but I found this was the most intuitive to help the transition from what you've studied way back in Calc 1 to what we're studying now. You can see this is our setup here from A to B. And this is on a loop, so it'll keep playing. But if you go just to Google and type in line integrals, Wikipedia will be the first thing that comes up, I believe. And this video will be off to the side. But it gives you a good representation, again, of what it is we're actually going to be finding without having to get too bogged down into the details quite yet. So I'll let you guys play around with that on your own time. I'll go ahead and pause this, and we'll jump back in and take a look at an example. All right, so the first example we'll look at here is going to be given our function f, given our vectored valued function r of t, which is going to be the smooth parameterization of our curve on the interval 0 to pi. And so the blue stuff that I have here, that's going to be the same setup that I had on the previous screen and that the video set up for us as well. So it's really not a very difficult process. We would take our x, our y, and our z, and we would plug those in right there to get this guy. And then we still will need the magnitude of our derivative here. So that's where I'll go ahead and start. So r prime of t. So I know it's been a while since we've dealt with vectors, but I'm just going to go term by term, taking the individual derivatives. I've got a negative sine t. I've got a cosine of t. And I've got a 1. I'll need to take the magnitude of this now. And if you remember that, that's going to be a big square root of this thing squared plus this thing squared plus this thing squared. So that'll be a sine squared of t plus cosine squared of t plus 1. We know that sine squared plus cosine squared is 1, so this whole thing just ends up being the square root of 2. So the setup here then will be the integral from 0 to pi. Remember, this is going to be with respect to t now, and t is bounded between 0 and pi, so 0 and pi. Then we've got our function evaluated at r of t. So when I plug in my x value there, my y value there, my z value there, that's going to give us a 2 cosine t sine t plus the square root of t, followed by that square root of 2 dt. So that value right there was going to be our square root of 2. And so from here, you would just integrate as usual. There is, in fact, an identity here that you could make this a little easier on yourself. If we go 0 to pi, that's going to be sine of 2t, and that will be the t to the 1/2. You could pull the dt, not the dt, excuse me. You could pull the square root of 2 out with the dt there off to the side. And then pretty simple integral at this point. This would turn into a negative 1/2 cosine 2t and then plus 2/3 t to the 3/2, needing to evaluate that from 0 to pi. Final answer here comes out to be 2 root 2 over 3 times pi to the 3/2. And so again, when it comes to thinking currently what that number represents, I would encourage you to go back and visualize that video, how we have our surface, we have our curve, it's going to have some contours in it, it gets stretched out, and again, the integral will always come back to area under a curve in its most fundamental form.